Hi there. So today we get into Chapter 7, Introduction to Work, Energy, and Energy Resources. So energy plays an essential role in everyday events and scientific phenomenon. We know there's energy in food, there's energy needed to run our cars, there's energy in the sunlight that warms us on the beach. Conservation of energy, which is the principle that energy can neither be created nor destroyed, is based on experiment. And some really cool examples of experiments. Well, and normally I don't recommend that you watch these videos, but at the bottom of this page, there's one of these overproduced OpenStax videos. But this one actually is kind of interesting. So the idea with roller coasters is that there's no engine on them. What happens is there's a chain which brings you up to a certain height, and then they just get released. So there's potential energy, mgh, at the top, and then it gets converted to kinetic energy, 1/2 mv squared, and they talk about how mechanical energy plus is potential energy plus kinetics. Take a look at that. So section 7.1 introduces energy. First time we really come to terms with energy in a physics context is with work. What is work? So there's an idea here with this lawnmower, is that this person is doing work on the lawnmower. And it involves two things. One is that there's a force applied to the lawnmower, and the other is that the lawnmower has to move some distance. So if you were to press on the lawnmower, but it doesn't move, then we don't, in physics, we say that that isn't work. You're not transferring some energy into the object. But once it moves, then you're transferring energy. Your force through a displacement gives you this work. And there's actually a unit of energy that's based on the Newton times the meter, and that's called the joule. So 1 joule equals 1 Newton times meter, and in basic units, it's a kilogram times a meter squared per second squared. So that's the basic idea of work. There is this equation, 7.2 FD cos theta. So the F and the D are just the force and the displacement, the magnitudes of those two. And the cos theta term relates to the angle between the force and the displacement. So those are two vectors, right? So the force and the displacement, they're usually in the same direction if you're pushing something forwards, and then just work equals force times distance, because if they're in the same direction, theta is 0 and the cosine of 0 is 1. So the basic equation is just work equals force times distance. But you can also imagine lots of cases where the force that you're applying is not in the same direction as the displacement. I guess maybe if something's already got an initial velocity in one direction and you're trying to slow it down with your force, you can imagine the force and the displacement being in opposite directions. And so it's possible to actually get theta is 180 degrees, in which case cosine of 180 degrees is -1. And you can have negative work, okay, where your force is taking energy away from the object. That's usually when it's slowing down. And it's also possible, if you look at this one, this guy's carrying a suitcase in one direction, and the force he's applying is in a perpendicular direction. In that case, the force and the displacement have an angle of 90 degrees between them. Cosine of 90 is 0, so it's a zero work situation. Section 7.2 introduces the next kind of energy called kinetic energy. And this is defined here in equation 7.12. Kinetic energy is equal to 1/2 mv squared. V is the speed of the object. M is its mass, so the speed squared, 1/2. That gives you this kinetic energy, also measured in joules. Here it's a little easier to see. You've got kilograms times the meter squared per second squared. But they motivate this definition of kinetic energy by thinking about work. And they talk about something called net work. So net work is the work done by the net force on an object. And it does always tend to change the speed of an object. And in fact, you can prove that the net work is equal to the final kinetic energy minus the initial kinetic energy. And that's the work energy theorem. And lastly, section 7.3 is about gravitational potential energy, which is defined here actually as a change. So it's equation 7.27, the change in gravitational potential energy equals mgh, where h is the change in something's vertical position. So g here is 9.8. It's the acceleration due to gravity on Earth's surface. M is the mass, and h is something's change in position. So the idea here is that as something goes up, it has more potential energy, meaning that it could fall, and then that potential energy could get converted into other forms of energy, such as kinetic energy. And in fact, they motivate it here by talking about work done against gravity. It makes sense that if you pick something up, you're pushing it upwards, like this mug, push it upwards. I'm doing work in some displacement, so I'm adding energy to it. Where does that energy go? It goes into this gravitational potential energy of height. And this example is going back to that roller coaster video. If you start with V equals 0, kinetic energy is 0. But then if you drop down to a height of 25 meters below where you started, then your potential energy goes down. And so balances out by your kinetic energy going up. And so you can find, just through energy considerations, based on a change of height, if you assume there's no friction, you can get the final speed without knowing anything about the actual details of the shape of the track. Section 7.4 is called Conservative Forces and Potential Energy. Last time we talked about the gravitational potential energy, and one of the properties of gravitational potential energy is that when an object moves along some path, the change in gravitational potential energy only depends on the starting and ending points of the motion, and it doesn't depend on the details of the path taken. So there are other forces that lead to potential energies that follow that property, and these are called conservative forces. A conservative force is one for which work done by or against it depends only on the starting and ending points of a motion and not on the path taken. So we can define a potential energy for any conservative force. And another example of a conservative force is actually a spring that obeys Hooke's law. So we found that the force is equal to K times X, where K is the spring's force constant. If you find the work done by the spring, it turns out you can define potential energy that's stored inside a spring. So this is equation 7.42. If a spring has been stretched or compressed by a distance x, then there's energy stored in that spring, which then can be released, 1/2 kx squared. So for example, if you pluck a guitar string as well, you press a force in one direction over some distance, this is storing potential energy in the stretchiness of that string. And what's really useful is this conservation of what's called mechanical energy. So we define mechanical energy is equal to kinetic energy plus potential energy. And it turns out that mechanical energy is constant over various processes. So you can use that to solve problems. For example, this car starts by compressing a spring. The spring stores the spring potential energy. Then it is released. That's converted to kinetic energy of the car. We could define the initial gravitational potential energy of the car to be 0 at this 0 height. Then it goes along these two different paths and ends up at a height of 18 centimeters above its initial point. Well, if you're asked for how fast the car is going at this point and in this point, you can use conservation of mechanical energy, and you don't even need to know the details of this path, as long as you assume that there's no friction, so there's no energy dissipated during the motion. Energy Skate Park is a fun PhET exploration. You can place a skateboarder up on a slope, and this little pie chart shows how much of her energy is potential versus kinetic. Well, if you release her, then down at the bottom here, if you release with fully kinetic energy and go down to the bottom, then it's almost all kinetic energy at the bottom, and then that goes up, converts to almost all potential energy, and she slows down, etc. So this pie kind of shows it's all kinetic at the bottom of the slope, and it's almost all potential at the top of the slope. Now, section 7.5 is called non-conservative forces. So I have sometimes been talking a little bit about friction and saying, we can only solve these problems if we assume there's no friction. That is because friction, kinetic friction in particular, is a non-conservative force. I also call this a dissipative force. It means that this mechanical energy is no longer constant. It gets taken away and converted into thermal energy. Another example of a non-conservative force is actually from an engine. If you're burning fuel in a car's engine and step on the gas, that takes some energy and from the fuel and adds it, and you gain kinetic energy, and so you actually increase the mechanical energy. So anytime the mechanical energy is not conserved, it's because there's some sort of non-conservative force that's acting, such as friction or engine force. So for example, you can imagine if there's only conservative forces involved, like the spring, if you drop a rock, it'll bounce back up right to the exact same height, and you can use conservation of mechanical energy. But in real life, if there's no spring there, if you just drop a rock, it might go boom and hit the ground and have a little deformation on the ground, and it'll just stop there. So in this case, mechanical energy is no longer conserved. It starts out high and then it ends up being zero, right? So you can split your net work into the work done by non-conservative forces plus the work done by conservative forces. That can be useful sometimes. And the work done by non-conservative forces is equal to the change in your total mechanical energy. So equation 7.58, instead of just saying E initial is equal to E final, you can say that E initial plus the work done by the non-conservative forces is equal to your final energy. And there's just some examples there where you tend to see that the friction force takes away energy. So you subtract it from the initial energy to get the final energy. This is one of the most important laws of all of nature, which is that total energy is constant in any process. It may change in form or be transferred from one system to another, but the total remains the same. So what you're doing is you're adding up all the forms of energy on the left-hand side of the equal sign for initial energy, and then you're adding up all the forms of energy again for some final situation. And they have written a bunch of terms here. So KE is kinetic energy, PE is potential energy. So kinetic energy, the energy of motion. PE is the energy of position, like from a spring or from gravity, a conservative force. WNC, so that's the work done on a system by non-conservative forces. So that can increase your final energy. So you put that on the left-hand side here. So it's positive if you're doing work on the system. It's negative if the system is losing energy by doing work on the environment. OE is other energies, so it could be a lot of different things. And they give you some examples: electrical energy, chemical energy, radiant energy, nuclear energy, thermal energy is another one there. All this stuff's important. So basically, a lot of times, some of those terms are zero. And so a typical equation you end up with is just the mechanical energy. KE plus PE initial equals KE plus PE final. But this is the more general equation. So they talk a little bit about transformation of energy. These are systems where something happens and some amount of energy is transferred. So the Big Bang, 10 to the 68 joules were transferred. I don't know where that comes from. Supernova, this makes sense. Yeah, you got about 10 to the 44 joules released. There's all these different things. A barrel of crude oil, when it's burned, produces this much joules. A ton of TNT when it's exploded. So all these things. Daily adult food intake recommended is 1.2 times 10 to the 7 joules. All of these things are for our energy. They talk about efficiency of a process. So if you are trying to do something, usually there's a certain amount of work output that you want, that you're trying to get. And then there's the energy you have to put in to get that. And so if you get out exactly all the energy you put in goes exactly into what you want it to do with no losses at all, that would be 100% efficiency, 1. So you take this number, multiply it by a percentage. But really, Like, for example, cycling and climbing, what that does is it produces a lot of these other energies, like thermal energy, which doesn't end up being used for what you're trying to do, which is cycle somewhere. So cycling and climbing is 20% efficiency. Swimming is a 2% efficiency process, okay? You're putting a lot of energy into churning up the water and all this stuff, and you are going somewhere, but it's 98% of your energy when you're swimming is just going into making the fluid go around in the swimming pool, and it's not what you're trying to do. If you get off the surface, you can double your efficiency if you swim underwater. Okay, electric motor is 98% efficient. Okay, so that's why electric cars are probably a good idea. One of the reasons. Section 7.7 is on power. So they talk about the word power. Okay, so this is what we mean in physics. Power is the rate at which work is done. W divided by T. So W is in joules, T is in seconds. The SI unit for power is called the watt, where 1 watt equals 1 joule per second. So if you use this equation, have work done in joules, time that it took in seconds, then you get the power in watts. They give you some examples. A 60-kilogram woman runs up 3 meters of stairs. She starts from rest, but has a final speed, so she's gained kinetic energy and gravitational potential energy, and she did it in 3.5 seconds. So you just divide. So they're saying that the work done is equal to the change in energy. So they put the energy on the top here, and then divide by 3.5, and you get 538 watts. Okay. It's impressive that this woman's useful power output is slightly less than 1 horsepower. A horsepower, as you may have heard of outboard engines or something being rated in horsepower. Horsepower just means 746 watts. People can generate more than a horsepower with their leg muscles for short periods of time by rapidly converting available blood sugar and oxygen into work output. But a horse can put out 1 horsepower for hours on end. So that's where it's an old unit of power. There's a bunch of examples in this table. A supernova at its peak is producing 5 times 10 to the 37 watts. Okay, the sun produces 4 times 10 to the 26 watts. Okay, so the sun's like a big light bulb, a 10 to the 26 watt light bulb. A lightning bolt. They have an actual light bulb on here somewhere. A 60 watt light bulb. Okay, it reuses 60 watts of heat. Person at rest is 100 watts. That's kind of interesting. We're all light bulbs in a way. A pocket calculator uses 1 milliwatt. Okay, that's why you can run it for so long on a little battery. And there's solar-powered calculators as well. So you can rearrange the equation for power to solve out for energy. Energy is power times time. And electricity bills are actually measured not in joules, which you'd think you'd pay for the joule. Turns out you pay for the kilowatt hour, which is a number of joules. 1 kilowatt hour is the amount of energy used if you're using a power of 1 kilowatt over 1 hour of time. So 3,600 seconds times 1,000 is 3.6 million joules is 1 kilowatt hour. Okay, so you do pay for the joule. It's just the joules are so small. They use kilowatt hours. It's a little more convenient. And so there's, for example, a cost of electricity in your region might be 12 cents per kilowatt hour. So you can figure out the cost of your electricity. Okay, yeah, so these last couple sections are a little weird. Section 7.8 is about work, energy, and power in humans. So they're talking again about this other energy. So this flowchart is basically about, it's about dieting or something. So you got your food that you eat. That's some energy. Well, you got exercise, which is your work, that expends. You've got your metabolic rate. No matter even if you don't exercise, you're going to use some energy. If you've got more food than you use up in exercise and your metabolic rate, then the excess can be stored as extra fat. Okay, so you can store energy that way. So that's what this is showing here. They're saying that the work, remember, when you put this WNC, work due to non-conservative forces, on the left-hand side, that's work done on the system. So when you exercise, you're doing work on the exercise equipment, right? So another way of putting that is that the exercise equipment is doing negative work on you. So they give a negative number here, but anyway, you minus it. And they give you some power consumed by different parts of your body. Anyway, it's just good to kind of skim through this. Some of these numbers are kind of useful in some of the problems. And then the last section is world energy use. And they talk about renewable and non-renewable energy sources. And now, I don't know if there's some sort of Republican Party lobby or something that is, working at Rice University, but this entire section does not mention climate change and does not mention greenhouse gases. Okay, but let me tell you, the most important thing about this is that there's two ways of creating energy. You can use fossil fuels, oil, natural gas, and coal. This produces pollution in the air, which then can change the Earth's climate. Okay, that's bad. Like, for example, carbon dioxide in the Earth's atmosphere. What that does is that traps infrared rays and changes our climate. And there's other things like water, wind, solar. Okay, those do not create nuclear, does not create greenhouse gases, and so does not affect our climate. That's, I think, the most important thing about this whole section, and it's not mentioned once. I don't know why. They just talk about renewables and non-renewable. Solar, there you go. Solar, not producing any greenhouse gases. That's good. Nuclear does not produce any greenhouse gases. It produces a lot of other bad stuff, but, so long term, nuclear can be bad. Short term, nuclear, I think, is actually good because it reduces our reliance on like coal, gas, oil, which are polluting the air and causing this climate crisis that we're in. So that's, I don't think that's an opinion. I mean, it's my opinion. It's not in this book. It is the opinion of all the atmospheric physicists that I work with here at University of Toronto. So I thought it was important to mention that. Conserving energy, but also I think it's important to try to rely upon energy sources that do not pollute the Earth's atmosphere. And that is the end of Chapter 7. My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.